we continue to study ODEs without finding the solution, finding a formula for the solution. We still don't have the techniques yet. We're just studying the ODEs by sketching, trying to sketch the graph of the ODE, a graph of the solution of the ODE. So here's an interesting example. This is a first order ODE. We can isolate the derivative in one side, and on the other side we put everything else. And notice that previously we had an expression that could have y, x, right? And we would perhaps draw points and have a column for x, column for y, and then a column for the derivative, and we plot points and see where the derivative looks like. So then we can draw those little arrows, right, to create that directional field where we can drop the little boat and see where the boat is going to go, right, describing the trajectory. That would be the graph of the solution. Now, this particular example, if you notice here, the right-hand side, it doesn't have any x. It's just an expression that has y. Okay, so that's why I wrote f of y, because it should be an expression that has only y. Well, if that's the case, it means that it doesn't matter what x is. The derivative stays the same for that particular y. For example, let's draw here a xy plane, and I'm going to see, this is the y-axis, x-axis. Let's say, for example, let's pick y equals 2. Okay. Well, I don't know what the derivative is there. Okay. So the line y equals 2 is here, but I don't know what the derivative here, the original derivative is here. But notice that if, let's suppose that the derivative, suppose the derivative for y equals 2, suppose the derivative, right, you plug y equals 2 here and you get a number. Okay, suppose it's 1, derivative is 1. That means the slopes are like that, 45 degrees, and they will be the same. It doesn't matter what x is, right? So if x is 1, it doesn't change the derivative. It's always 1. Y doesn't change because there is nothing to plug in here for x, right? If x is 1, this expression is still the same. Okay, it's still the same. If x is 5, this expression is the same. So suppose the derivative is 1, then it will be 1 in any part of that line, right? I can draw the 45-degree slopes throughout the whole thing. If I pick a different y, perhaps here y equals -1, again, I don't know what the derivative is. If I plug y equals -1 here, I don't know what it is. But suppose for y equals -1, suppose the derivative is, when you plug, right, you plug y equals -1 there. Suppose it's, let's say, suppose it's -1. Okay, I don't know what it is, but let's suppose it's -1. That means that the slope will be like this throughout the whole line for y equals -1. Again, it doesn't matter what x is because x doesn't change this. Only y changes. Only y can change this. So it doesn't matter if x is 1, 2, the derivative is always the same. So for autonomous ODE, that means the derivative does not depend on x. So that means you have, when you pick a horizontal line, the derivatives will always be the same. Pick another horizontal line, whatever the derivative is will stay the same. Now, what it's interesting is that if in one place all the derivatives are positive and in another place all the derivatives are negative, well, somewhere here in the middle, the derivative has to cross 0 because it was positive and then down there is negative. So if it changes from positive down here to negative, the derivative has to pass through 0. So there's a place here somewhere where the derivatives are all of them are horizontal. And that's where the derivative is 0, right? Those are called critical points. All right, let's take a look at one example. Here is dy dx, and this would be y squared equals -1. This is an autonomous ODE. Why? Because the derivative is in terms of y. It doesn't have any x in there. All right, let me make a little table here and see what happens. Just like we did before, we draw 3 columns, 1 column for x, 1 column for y, and 1 column for the derivative, and see what happens. Notice that if x is, let's say if x is 1, the derivative is y squared minus 1. If x is 3, the derivative is y squared minus 1. Notice that it's always the same. Whatever y is, it will be y squared minus 1. So in fact, if x is anything, the derivative is y squared minus 1. Okay. So let's suppose then x can be anything. Suppose y is 1. Well, then the derivative would be 1 squared minus 1, which is 0. So let's pick, see, I don't care about x because x doesn't change anything. So let's pick y equals 2. This would be 2 squared minus 1, right? And then this would be 3. And pick one more. X can be anything. And then let's pick y equals -1. This would be -1 squared minus 1, 0. So this is, we have 2 critical points here. See where if y equals 1, the derivative is 0. If y is -1, the derivative is also 0. Let's look at the graph and see what happens. Okay, so here is y equals 1. Let's draw y equals 1 here. So this is along this line, right? If y equals 1, the derivatives are 0. So I can draw the arrows like this. Again, the arrows represent the slopes at those points. We don't know what the original function is, what the y equals something is, right? We don't know what the original function is, but we know the slopes. And if the function crosses here, if the function is here somewhere, the slope is 0. If, let's say, y is 2, now we're in this line. This means that the slope is 3, so the derivative is very steep. It's almost vertical, right? It goes upward like that. Okay. And then if y equals -1, which is right here, the derivative is also 0. So I can draw the arrows here. Let's pick one more point. Let's see. See if y equals 2, the derivative is 3. If y equals 1, the derivative is 0. And then if y equals -1, the derivative is 0. That means in between, right, between this one and this one, we don't know. Let's see what happens. Let's pick y equals 0. If y equals 0, this would be 0 squared minus 1. The derivative is -1. So if y equals 0, the derivative is 45 degrees downward like that. Okay. So notice that we're starting to see the direction of field, and one thing we can do to make sure that we don't have any other places that where the derivative is zero is to try to find all of them. Do you think there is more places where the derivative is zero? So here's one, here's another one. If we can find all of them, then we can look at between each of those solutions to see what the derivative is and then draw them. So let's set the derivative equals zero. Why do we want to do this? So we can find the critical points. Okay, so the derivative is y squared minus 1, right, according to the ODE. So if we set this equal to 0, this means that y plus 1, y minus 1 equals 0. So those are the two solutions. So those are the two critical points. So that means we only have these two places. There's no other places where the derivative is 0. So that means that between here and here, right, between y equals 1 and y equals negative 1, there is no derivative equals to 0. So it's either negative or positive, but we already know it's negative here because we picked y equals 0, right? So that means that between here and here, the derivative should always be negative, right? Then we pick a number above this 1 here, y equals 1, and if we pick 2, the derivative is 3. That means above that critical point, the derivatives are positive. Let's see what happens if we pick a point down here, negative 2. So at negative 2, this would be negative 2 squared minus 1. This is 4 minus 1. This is 3. The derivative is also positive. So along this line, the derivatives are also steep like that. And this means that below that critical point, y equals negative 1, the derivative is positive. Now, below the negative 1 mark, could the derivative be negative someplace? Maybe if we go down further, could it be negative? The answer is no, because if to be negative, right, we already know it's positive here at y equals negative 2. To be negative, that means the derivative has to become negative passing through 0. But we already found these two. There are only two. There is no other place where the derivative is 0. So that means that guarantees that below y equals negative 1, all the derivatives are positive. Now we are assuming that the derivative here, obviously this is continuous, right? Continuous means there's no jump. You don't jump from positive to negative or vice versa. So there's no jumps in there. So we do this, and then we can draw the solution lines, the graph of the solution. So if we drop a little point here, this point, if I'm close here, that means this point is going to go to horizontal a little bit, but eventually it's going to go down, then it's going to cross here, and then it's going to reach this part, and it's going to do something like this. So the solution, this is one solution. What happens if I drop the point right here? Well, then, see, it's going to the right, and then this is going to eventually go like this. Same thing if I drop something here, then it's going to go like that, right? So these are different solutions, all the same family of solutions. And there's one more case here. If I drop something here, then it's going to go like this, right? If I drop something here, it's going to go like this. So all of these are solutions. So this is one solution. This is another solution. This is another solution, right? Several solutions. And again, we don't know what the graph is. So this is a function. This is a solution. Here's another one, another solution, right? Another solution here. So several solutions. And we did all of this by finding, so the idea is to find the critical points where the derivative is 0. So find one critical point here, another critical point, the derivatives are always 0. And then in between, above and in between each pair, pick a point to see if the derivative is positive or negative. Then you can draw the arrow. Okay. So let's take a look at one more example. So here is let's take a look at this one. This is y squared minus 4. So first step, this is an autonomous ODE. So let's find the critical points. So the critical points, we set the derivative equal to 0. This means that y squared minus 4 equals 0. This means that y, the solution would be negative 2 and 2. Okay, gonna draw, make a sketch here. Here is 2. Here is negative 2. These are the only two places where the derivative is 0. Okay, so I'm going to draw those arrows to represent that the derivative is 0 at those points. Okay, now we need to pick a point in between those two. The easiest one would be at 0, right? Let's see what happens at 0. Notice that I don't care about x because x doesn't influence anything in here, so I just pick y. So here at 2 and negative 2, we know the derivative is 0. Let's pick y equals 0. If y equals 0, then this would be y squared minus 4, right, according to this. That's negative. So the derivative is negative. It's very steep at those points. So it's kind of like this, right? And that means between here and here, the derivative is negative. Maybe here is less negative. Here is less negative, but it's negative. Okay. Let's see what happens above the 2. Let's pick y equals 3. This would be 3 squared minus 4. Okay, so that's 9 minus 4. This is 5. So if I pick 3 here, then the derivative is very, very steep. It's 5. Right here. And let's pick a number below negative 2. Let's pick negative 3. This would be negative 3 squared minus 4. Right, I plug y equals negative 3 here, and I get 9 minus 4 is also 5. So if I pick negative 3, the derivative is also very positive. Very positive. Okay, I think we are ready to draw some solutions here. I'm going to use green here. Okay. All right. Right. Notice by looking at the arrows, I can tell that the solution will be something like this. There we go. And right, something like that. And if it's here, it's going to go like that. So the function goes up very quickly here because the derivatives, the arrows here, pointing almost vertically. So maybe we'll do something like this. And if I pick a number here, then it's going to go this way. It cannot go down because look at the arrows. They're positive. So that means it's doing something like this. So those are some of the solutions, sketching some of the solutions. Let me draw this XY plane again. And this time, I'm actually going to draw just the Y axis, like that. And what I'm going to show you now is that this is called a phase portrait. A phase portrait, it just tells us how the derivatives look like for different types of values of y. But we need to include the critical points there. So we found critical point at 2, right, at negative 2. So those places is where the derivative is 0. So for the phase portrait, so this is called phase portrait. So I'm going to write here that the derivative here is 0, 0. And then above 2, the derivative is positive. So this means here it's going up to represent that above that line, the derivatives are positive. And then in between, if you look at what's happening here, in between the derivative is negative. So I'm going to draw an arrow pointing down. And then below negative 2, the derivatives are positive. Okay, so the phase portrait gives us an idea of how the solution is behaving, right? So here, if I drop something in this between these two lines, then the solution is going to go down. And then if I drop something below the negative 2, the solution is going to go up. So we actually have special names for these. This is called the y equals negative 2 is called an attractor. And then this solution here, not solution, but when y equals 2, this is called a repeller, for obvious reasons, right? So at that particular point, look at the solution, look at the phase portrait. Anything above will push the solution up. Anything below at y equals 2, the solution will be pushed down. So it's repelling. And then at y equals negative 2, it's attracting. Anything above will go towards it, and anything below will go towards that same place. So it's one way to classify the critical points.